Awesome. Hi, everyone. My name is Leo. I'm VP Engineering here. And we're going to take a quick tour through history to figure out how to build better products and how to do it quickly. And so to do this, we need to be able to do three things. One is we need to work in cycles, we need to use the data, and we need to pick the right people. And we'll talk through all of these fairly quickly in these 15 minutes. And if you have questions, would love to hear them at the end, and we'll answer any of them as I can. So the first thing we need to think about is working in cycles. And in order to really understand this, we need to go back to the Korean War. So Korean War, early 1950s, North Korea fighting South Korea. The US enters the war on the side of South Korea, seeing it as a battle of communism versus capitalism. And a lot of things happen, but one of the biggest ones is this is the first time that jets are used in air combat and are fighting other jets. And so the Soviet Union builds the MiG-15, and the US says, okay, cool, we need a jet to fight the MiG-15, so we'll build a completely different looking aircraft. Oops, they built almost the same thing. But that aside, even though they look very similar, there are small differences, as there are any time somebody builds, something similar. There are differences between a Ford truck and a Chevy truck. And the differences between them would seem like they're biased in one direction. The MiG-15 climbs faster, turns faster, and is a much more maneuverable aircraft. And traditionally, that had been associated with being a better fighter plane. And so, everybody looking at this said, okay, well, the MiG-15 is a more maneuverable aircraft. It's totally going to win in the skies, and we're going to have to deal with that. But what actually turned out was, as the Korean War wore on, the kill ratio for the F-86 was much, much higher. So, the US Air Force claims it was around 10 to 1. Realistically, the number was probably close to 3 or 4 to 1. But the F-86 outperformed and was much more successful, much more effective than the MiG-15. And this was a mystery at the time. Nobody really understood it. It just happened. And, some folks said Americans were better trained. There were a lot of ideas being explored. But there were small little things, that differences between the planes, and that nobody really thought of at the time that were the reason for this. One of them was that the F-86 had hydraulic controls, and the MiG was operating with manual controls. So this is the equivalent of having power steering in your car versus having manual steering, where it's purely mechanical. And so it took one person to figure this out. Enter Colonel John Boyd. So as you can see in the picture on the left, John Boyd was a fighter pilot. He earned some pretty intense nicknames: 42nd Boyd, Genghis John, Mad Major. He was a fighter pilot's fighter pilot. But as he got older and as he got out of actually sitting in the cockpit and exchanged his flight suit for a business suit, he started thinking about what actually happened. And why was it that the US aircraft was much more effective when traditional dogma says, oh, the MiG should have been much better? And what he realized was that the fact that it had hydraulic controls actually really made a huge difference. And he was the first to come up with this thing, what he called the OODA loop. So this is one of his original diagrams, and there's definitely some goofy things and 5-pointed stars and a lot of things here. But basically said, look, a fighter pilot's job is to do 4 things. They observe the situation around them, they orient themselves, they decide, and then they act. They figure out what they need to do, they make the decision, and then they actually have to go do it. And this can be simplified into sort of this OODA loop. And it turns out this applies not only to fighter pilots, this applies to a lot of other things as well. And the basic idea is the faster you can do this loop, the more effective you're going to be in terms of creating your product, in terms of dogfighting, in terms of anything you're trying to do. And this idea was interesting and novel, and so it came to be called Boyd's Law. And the basic form of Boyd's Law is speed of iteration beats quality of iteration. And the reason why the F-86 was able to do faster iteration was because of the hydraulic controls. Because of those controls, the longer the dogfight went, the more and more tired the MiG pilot got. And so their OODA loop slowed down. As they were more exhausted, as they spent more time thinking about what they needed to do, this made a difference over time. While the F-86 pilot, the American pilot, with their hydraulic controls, stayed fresh, stayed relaxed. Obviously the ton of tension of the dogfight going on, but they were able to more effectively iterate and make decisions quickly. So what does this mean from a product perspective? If you've worked with any sort of agile approaches on building software, they recommend iterations no longer than 4 weeks, just making smaller, tighter cycles that you can iterate quickly. It means that functional specifications are best when they're concise and evolving. You don't know what you're going to discover as you make small sprints. So it's really impossible to come up with a complete, fully functional design up front. And the best way is sort of to accept that and iterate as you go. And then the last piece that's important here is software testing. There's a lot of ways to think about software testing, and most of us don't work in situations where if our software doesn't work, people die, or there's some sort of very, very top level critical thing. And so software testing is really about trying to fail as early and as often as possible to try and detect errors that would be more painful further down in the cycle. And these are all ideas that come out of this, that you want to speed up your iteration rather than try to make your iterations more high quality. Now, this doesn't mean you should give up on quality altogether, but it does focus that speed is the more important thing to think about. And this has been used successfully, by all sorts of companies, from video games to manufacturing to other software companies. And it's a general idea that's more and more effective as folks approach it. So now that we know how to work in cycles, one of the critical things to work in cycles effectively is to have the right data. If you don't have the right data, then you're not necessarily orienting correctly, you're not necessarily making the right decisions, and your actions aren't the right thing. So we're going to then dive into understanding how it is that, how you get data and what you want to be careful about and what you want to be thinking about. And to do this, we're going to have to go to another wartime situation. We're going to have to go back to World War II. So World War II, the US enters the war and realizes that, it's fairly unprepared to fight a massive conflict in Europe and in the Pacific. And so to have the battles and to prepare, the US immediately says, okay, we're going to need to make a bunch of tanks, we're going to need to make a bunch of bombers, and we're going to need to, well, make a bunch of science. So this is one of the things that the United States realized early on was the ability to use science and mathematics to solve a lot of the challenges of the battlefield and a lot of the challenges of modern warfare that had not really been applied. Science had always been a part and there's always innovation, but in World War II was really the first time when the US said, we're going to take a lot of scientists and we're going to start giving them practical engineering problems that soldiers are running into or the Navy is running into, and we're going to have them try and apply math and figure out what that looks like. So in practice, what this means is the US created the Office of Scientific Research and Development. Sounds wonderful. Sounds like, they're going to science the shit out of things. But the OSRD wasn't exactly, okay, we're going to do all sorts of good, nice things. They did a bunch of things that we would look back on and say, this probably was not cool. They said, cool, you're a conscientious objector? Great, we're going to use you for frostbite experiments or seawater experiments or temperature extremes. Or, let's see how dirty you can get before you can't tolerate it, because we want to have science on what soldiers can do in the field. And as part of the alphabet soup, the Office of Scientific Research and Development created the National Defense Resource Council, which in turn had the Applied Mathematics Panel, and that had a statistical research group. So one of the big things that the US did was they outsourced this sciencing to a number of major universities. And the statistical research group was right here in New York at Columbia University. And it was a number of mathematicians that were working on a bunch of different problems that were important to the war effort. So for example, things like, how should you shoot torpedoes? What spread should you use when a ship is zigzagging and you want to optimize the chances of actually hitting the ship? Or another problem that came up was where to put armor on the bombers. A lot of bombers were flying into Europe, were flying over Germany, and a bunch, were not successful in their missions. So here's a bomber from before. The problem is if you send a bomber over enemy territory, especially if you do it during daylight, which you need to do because you need to be able to see where you're bombing, sometimes your bomber gets shot down. And this is a problem. Even though America is the arsenal of democracy and could build hundreds of bombers coming out of the Boeing plants in Seattle and other places, they can't afford the crews and the bombers, and they needed to figure out how to make the bombers more effective. So what did they do? The bombers that came back, they assigned people to go and count all of the bullet holes in them. Possibly the conscientious objectors from before, possibly it was, some random private's job, but they would go in and they would create maps for every bomber that came back and said, okay, this is where all the bullet holes are on the plane. And now here's all the planes that came back, and these are all the bullet holes. And they sent this to the mathematicians at Columbia and said, okay, you guys tell us, where should we put armor? And the mathematicians looked at it and they were like, well, it's obvious. Look, there's the bullet holes. Find the spot with the most bullet holes and put the armor there. And they're about to send this recommendation back to the U.S. Air Force, to the Army Air Force, when a young mathematician by the name of Abraham Wald was like, whoa, 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 slow down, guys. That's actually the absolute wrong thing to do. You have limited armor. You can only put it in a few spots. You can't armor the entire airplane. But if you put the armor in the spots where there are the most bullet holes, you are going to kill people. This is the worst idea you could think of. And the reason for this is really simple. When we look at it in hindsight, that reason is something called survivorship bias. What this means in this case is the folks counting the bullet holes only see the planes that came back. They don't see the planes that crashed. So all of the data they have is severely, severely biased by the planes that did not crash. And the reality is, if you think about it, this bomber is up in the air, somebody's shooting at it from the ground. They're not precisely targeting one small part of it. And so really the bullet holes should be randomly distributed across the entire airplane. And the fact that you're seeing a design like this where they're not, the data like this, what this means is these are the places in the airplane where it can take bullet holes and still return back to base. And the planes you're not seeing actually have the bullet holes in the places where there are no bullet holes on the plane back, on the planes that came back, which means those are actually the spots you want to armor rather than the spots where you see the bullet holes. And this insight, saved hundreds of lives, thousands of crews, hundreds of bombers, and thanks to this representation of survivorship bias. So most of us are not flying bombers over dangerous territory. What does this mean for us as we look at our data? Here's a couple of common examples that we see in the world. So the first one is, you look at Gates, Jobs, Zuckerberg, they're all college dropouts. So yes, that must be the way to become fabulously successful. It isn't, because you're not looking at all the other college dropouts or folks that abandoned their education. And on average, your odds are less great than you are if they completed college. Classic thing to think about is, you think about old cars or old records or old appliances and you say, oh, they don't make them like they used to. Or old music. But what you don't see is all of the car models that didn't make it 30 years, all of the music that nobody listens to at this point. All of these are survivorship bias examples. So when you look at something old, you only see the ones that were actually really good and that made it survive through this time. You don't see all of the ones that are no longer existing. And another one that's relevant to software engineering is you work in the features sometimes that your existing customers want, whereas you're applying survivorship bias for the customers we have now. Now, obviously we want our customers to be successful and we want our future customers to be successful, but it's important to balance these and think about how we're distributing our work and how we're doing stuff to make ourselves more effective and move faster in terms of the projects we build. So we now know about working in cycles. We now know about using data. The last piece that we need to think about is picking the right people. And to pick the right people, I wanted to play this quick video. This is from Meet the Johnsons, and hopefully this plays and you get a little bit of audio, but there's subtitles too. So the point of that clip was, it was not a very well thought plan to send a dinosaur with a big head and really tiny arms to grab a boy. And we all understand this intrinsically. We want to find the right people for the right jobs, but that's a challenge. And what is a good framework we can use to think about who are the right people for any particular job? And so enters this guy by the name of Simon Wardley. He has no connection to anything military that I could find, not World War II, not Korea, not Vietnam, but still, I think he's relevant to our talk. And the reason he's relevant is because he came up with a conceptual framework that sort of intuitively makes a bunch of sense, but is super valuable as you're thinking about the right people for the right job. And this framework is called Pioneer, Settler, and Town Planner. And we intrinsically understand that these are different roles. And these roles are all equally important. Pioneers, settlers, town planners, they're all brilliant people, but they excel at different things. The pioneer excels at taking stuff from civilization, going out and surviving in the wilderness. You know, they just have to make it through the winter. The settler then shows up the next spring and says, okay, look, we're going to be here for a couple of years and should build some cabins, maybe plant a field or two, starts thinking about that. And then eventually, as the town grows, you want to start thinking about garbage systems and sewage and elections and electrical systems. And these are three different roles. And thinking about your project and thinking about your company, they require a different mix of these roles. Some projects might all be pioneers with a tiny bit of settling and town planning. Other projects might require a lot of settler work. And they'll ask, you know, larger projects may require town planners, and a pioneer is not going to be happy and not going to be effective on that team. So none of these are, you know, better or worse than any others, but it's important to understand when you're building a product and you're doing your rapid iterations and you are using data, do you have the right people with the right attitudes and the right perspectives to do these projects? And how do you, in terms of using this framework, thinking about what does my product actually need, which people do I have, and do we have the right archetypes on this project? Cool. So we've covered three major pieces of thinking about faster and better products. First, work in cycles. Second, use data. And third is pick the right people. And I want to say thank you. You know, if we have a lot of openings, love for folks to come join us, or if you're customers, come work with us. We think about this regularly, and we try to apply this to make faster and better products to make our customers more successful.
Yeah, and thank you, Leo. And we don't have any questions, but I'm going to talk for just a second. So if you would like to slide in a question while I'm talking, you're still welcome to. But I want to extend that invitation to, if there's something you're building and you want to help, building that on BAS, we're always here. We have an extensive client services team. We have Leo. We have everyone. It doesn't need to be so formal. If you have a great idea, let's talk about it. You know, we are only as good as our customers, really. And unlike legacy DSPs, you know, it's not a matter of you plug in, you use us. Most of our customers are actually bringing something of their own to bear, and their success they drive on the platform is all theirs, rather than something that we're doing with some secret features or the black box that we have. So we're really passionate about helping our customers build what they build. And just a little housekeeping, we do have a webinar happening next week where we're going to be talking about why in 2021 it makes sense to have your own bidder. So I know that a lot of the folks on this call are already our customers, and so this may be kind of a review for you. But our CEO, Ari Paparo, will be hosting it, and he'll always be open to answering questions about any range of topics. So as you're thinking about 2021 and what you're planning and what you're building and what you're doing, this may be a good webinar for you. I'm going to go ahead and send that to everyone in the chat so they can sign up for that. And with that, Leo, I want to thank you for walking us through this. This is the first time I've seen this presentation. I know you've given it before internally, but I thought it was fascinating, especially the survivorship bias stuff. Actually, there was something circulating on Twitter about that. You know, if your big data team doesn't understand what this plain means, get rid of them. And everyone was dunking on them. But now I understand it. So everyone stay safe, and we will see you next time on October 1st for our next webinar with Ari Paparo. Thanks for tuning in.